escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the north and south poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Chelmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
Do you think we're gonna launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is gonna happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really a point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth.
Imagine you are on the moon. Your job for the next 8 hours will be exploring, traversing up and down lunar hills, sampling rocks, and setting up equipment. Temperatures can reach a blistering 250 degrees Fahrenheit. Luckily, you have a portable life support system, a backpack that provides oxygen, water, power, and, for the excruciating temperatures, a cooling system. Under the Artemis program, NASA and its partners are planning to return astronauts to the moon, and the agency is testing new spacesuit technologies. As a new age of exploration heats up, engineers are looking to improve how to keep astronauts cool in space. Outside the International Space Station, astronauts perform extravehicular activities, EVAs, also known as spacewalks. During the Apollo era, spacewalks took place on the lunar surface, and with the Artemis program, humankind will once again return to live and work in the harsh environment of the moon. Future plans call for spacewalks to last longer and be more demanding, not just on the astronauts, but also on the spacesuits and systems that protect them and keep them alive and healthy. NASA has been working on advanced technologies needed for next-generation spacesuits. NASA's reference design, the Exploration Extravehicular Mobility Unit, or the XEMU, features greater mobility, visibility, and flexibility. This prototype is just the beginning. To meet the needs of future exploration as part of the Artemis program, NASA will share its newest designs, research, and data with commercial industry, whom NASA will partner with to build the next-generation spacesuit. It is an effort that will benefit from NASA's most recent studies and the agency's 50-plus years of spacewalk experience. Spacesuits are essentially a spacecraft made for one. They have many important life-preserving components, but none is more complex than the system to regulate the temperature of the astronaut. Engineers call this cooling system the thermal control loop.
The thermal control loop is part of the portable life support system, or the backpack that the astronaut wears when they do an EVA. The thermal control loop is designed to keep the astronauts cool. When the astronauts are doing spacewalks, they can be exposed to extreme temperature swings, say up to 250 degrees Fahrenheit. The thermal control loop is part of a system that consists of a liquid cooling ventilation garment, or LCVG, that the astronauts wear under the spacesuit. It consists of tubes that are filled with water that circulate from water pumps in the backpack to keep the astronauts cool.
During the Gemini program, engineers realized that astronauts not only needed protection from the temperatures of space, but also from the heat generated inside the suit, from their own bodies as they worked. Originally, the suit designers thought that airflow over the astronaut's body would keep temperatures regulated. What they discovered was that air cooling in a spacesuit is insufficient to do that job. During the Apollo era, it was decided running cool water through a garment that covers the body could help keep the astronauts from overheating. The means of cooling the astronaut was now an essential life-sustaining element to the spacesuit and was here to stay. The spacesuit currently in use on the space station, developed in the 1970s, also uses a water-cooled garment. Circulating water is still the best way to cool an astronaut. However, improvements can be made on how to move that water through the system, using new technologies and materials to test how to make the essential cooling system safer and more reliable than ever before. The result of this research is SERFI, the Spacesuit Evaporation Rejection Flight Experiment, all the critical elements of a spacesuit cooling system in one box. 2 SERFI units have been built, one to work here on Earth in our gravity, and another SERFI unit meant to be tested in the absence of gravity, in space. On board the International Space Station, astronauts take advantage of the microgravity environment to perform a variety of science experiments and to test exploration technologies. When engineers developed the spacesuits for the Apollo and Space Shuttle eras, NASA did not have a space station in operation. Today, the station presents a perfect platform for engineers to use microgravity to put the SERFI cooling system to the test.
In that experiment, we will test a couple different versions of the water pump that will be used to circulate the water through the system. We'll test temperature sensors, we'll test pressure sensors, integrate all those into one little package and test them for long duration to see how they'll perform over the expected life of a spacesuit.
SERFI shows how the water will move through the system as if it were inside a spacesuit, cooling the astronaut. But a spacesuit cooling system needs to do more than just circulate water. As the astronaut works, their body generates heat, which is transferred into the liquid cooling and ventilation garment. A thermal control loop needs a way to remove the heat from the water that is circulating through the system. That's where SWIMMY comes in, the spacesuit water membrane evaporator.
SWIMMY consists of some porous hollow fiber membranes that are contained in a metal manifold. When warm water flows through the porous membranes and then is exhausted into space, the cool water continues through the porous fibers and continues to flow through the LCVG liquid ventilation garment to cool the astronaut.
With the means to run a cooling system and offload heat and gases, the SURFY unit runs for 8 hours at a time, the span of what a spacewalk might last in space or on the moon. The tests are run again and again, simulating the rigors of what a spacesuit thermal control loop might encounter during its life cycle. Astronauts take water samples from SURFY for analysis. Just as a spacesuit might sit in storage for a time between spacewalks, like during a trip to the moon or Mars, SURFY is sometimes switched off. This time of dormancy is when contaminants can grow in the system.
That's when the bugs, the microbes, grow in the water system. And those little guys grow and they reproduce and they can grow through the system. They'll clog your filters, and once your filters get clogged, the water stops flowing.
When the water stops flowing, the suit stops cooling. Contaminants in the water are such a problem for current spacesuits that astronauts set aside time for regular water maintenance chores every 90 days. The SURFY tests hope to demonstrate that new technologies and materials will be far more robust in working through water contamination issues, reducing the risk of the cooling loop failing.
We don't want to have to worry about water quality. We want to be able, we've joked among the team, we want to be able to pour chicken soup into the exploration EMU and it'll still run the way it's supposed to run. Even if there's microbes in there that the system doesn't care. So we want the filters to catch the microbes, and if the filters don't catch the microbes and they flow through the pumps don't even notice the microbes or the contamination or whatever's in the water. They keep operating the way they're supposed to operate. We want our crews to be spending their time exploring, not running maintenance procedures on our spacesuits.
All the testing for SURFY in space is duplicated on Earth, with a twin SURFY running in 1G, Earth's gravity. By testing here and simultaneously testing in the microgravity of the space station, engineers can infer how the cooling unit will run in the 1/6 gravity of the Moon, the 1/3 gravity of Mars, and all points in between. The knowledge gained from building and testing the twin SURFY units is already paying off, as work is underway building a full-size backpack for NASA's prototype exploration spacesuit.
How's it going to perform in microgravity? Well, by sending SURFY to space station, we can actually test how it's going to perform in microgravity. That in itself buys down the risk. So now there's one less unknown that we have to worry about when we send our hardware off to do what it's supposed to do.
I am so excited that SURFY, SWIMMY is on orbit, that we're working great, our ground unit is working great. SURFY has made a difference. We've had engineers, scientists, thermal analysis, water experts. It's been an exciting multi-discipline collaboration.
It's a collaboration that will inform spacesuit technologies for the Moon and beyond. A new design for a thermal control loop and its ability to help regulate temperatures for astronauts during exploration can benefit from the data gathered from SURFY, making it one cool little experiment.
In 1988, Dr. James Hansen, then director of NASA's Goddard Institute for Space Studies, stood before the U.S. Senate and testified that
global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. This last year, 2021, comes in as the 6th warmest year on record, and it continues this large, long-term warming that Jim Hansen was detecting even in 1988. And in 1988, that was also a globally warmest year, but now that ranks only 28th in the ranking. And so the warming that we've had since Jim Hansen's testimony has been dramatic and totally vindicates the concern and the warnings that he put out at that time.
The Goddard Institute for Space Studies, or GISS for short, maintains NASA's record of Earth's surface temperature, called GISS-Temp, that shows a clear and unequivocal increase in our planet's temperature. GISS-Temp stretches from 1880, long before NASA existed, until the present day. Now, when you think of NASA, you probably think of, well, space, right? And we do lots of work studying Earth from above. But the GISS-Temp record is actually built from the ground up. We collect measurements taken from weather stations, Antarctic research stations, and ships and ocean buoys all around the planet to understand what temperature changes look like globally. And why does the record start in 1880? That's the earliest period that we have sufficiently reliable measurements from ships and weather stations in enough places to be confident in the global record. Interestingly, it's also shortly after the time we call the Industrial Revolution, when humans started putting significant amounts of carbon dioxide in the atmosphere. But we'll get back to that later.
There are millions of measurements over the last 140 odd years. We put those together. We're using data from literally tens of thousands of different stations around the world. We use the information that's there to create a global picture of what's happening, and that gives us a very accurate estimate of how any year ranks, or what the anomaly is for any one year compared to what happened in the 19th century or what happened in the middle of the 20th century.
So we have our statistical reconstruction of Earth's recent climate, but in research science, we like to check our work. There are a couple ways we can do this. First of all, teamwork. Our colleagues at NOAA and at other agencies and universities around the world also create their own records, and we can line them up side by side and see just how closely they align. Everyone's independent climate records show the same thing. Earth is warming significantly and rapidly. And here at NASA, we have an even cooler way to check our work: space. Right now, we have more than 24 satellites dedicated just to studying our planet. Satellites can take measurements of the entire planet and line them up with our estimate of global temperature change. And sure enough, they also match. Our measurements from space match up well with what our analysis tells us. Earth's climate is warming. The next big question: why is our planet warming? Well, let's jump back to the Industrial Revolution. The release of carbon, mostly carbon dioxide, from human activities like driving cars, flying planes, and industrial burning of fossil fuels is responsible for the majority of climate change. Carbon exists in stores underground as oil, gas, and coal. When we burn it, we release it into our atmosphere, where it traps excess heat coming from the sun, raising the temperature. We've known for more than a century that carbon dioxide added to our atmosphere traps additional heat and is a major contributor to the greenhouse effect. So we can also track the concentration of carbon dioxide in our atmosphere, the primary cause of the current climate change. Both from space, using NASA satellites like the orbiting Carbon Observatories 2 and 3, and from the ground. If you've heard of the Keeling curve, you're familiar with one of these records. Researchers have been taking daily measurements of atmospheric carbon dioxide from Mauna Loa, Hawaii since the 1950s. From space and the ground, the signal is clear. There's a lot more carbon in the atmosphere than there used to be. Other things have changed too. We've chopped down tropical forests, caused the ozone hole, and filled the air with soot, smog, and other kinds of air pollution. And this is on top of natural variations caused by the dynamics of the ocean, or volcanoes, or variations in the sun's activity. And so we can ask whether it's human activities warming our 8 trillion calculations per second. We put these huge supercomputers to work to recreate Earth's climate. So we have thousands of ideas of what could naturally cause climate change. We have 4 billion years of history where nearly anything and everything you could imagine has impacted Earth's climate. But each of these events has their own distinct fingerprint, which we can identify, a pattern of behavior with natural variability. Using supercomputers, we can run simulations of natural climate drivers, solar energy changes, wobbles in Earth's orbits, ocean turnover, volcanic eruptions, and we can run simulations of human effects. And what we've seen is...
It's us. There's no way around it. Looking at the evidence, we're the force that's enacting these changes. I am so proud of our ability to understand the climate, but I'm terrified of what we found.
But it's not just the causes of climate change, it's also the effects. Because it's not just about knowing why our planet is warming. It's also about understanding and preparing for the effects of added warmth.
Measurement of global average temperatures is so important because it's one of the most direct indicators of Earth's changing climate. But the Earth is really a system of environmental systems: land, ocean, atmosphere, and ice, and changes in one system impact the others. Our oceans are our first line of defense in climate change because they absorb so much of the extra trapped energy in the Earth system.
We are seeing the impacts of climate change now. Now we know that as our climate warms, wet areas are getting wetter and dry areas are getting drier. For example, we see more intense snowstorms. We see slower hurricanes that are causing more precipitation that inundate land. And we have more extreme precipitation in the form of atmospheric rivers that come from the Pacific and reach our west coast.
The oceans are absorbing a large amount of heat because of climate change. And once that heat is in the ocean, it actually travels all around the planet because of the ocean currents. And that has impacts on local weather and long-term climate.
As the planet warms, it's not just the ocean that's warming, it's also the ice that sits in the ocean and on land. The ice on land being warmed increases melting, which is increasing freshwater input into the polar oceans and causing sea levels to rise across the globe.
So as the climate is changing, we really are seeing a lot of changes to the environment up in the Arctic. We're seeing more permafrost thaw when it's warmer up there. The warmer air temperature can lead to warmer ground temperature, and we get that thawing of that permafrost layer.
We're finding that the fire season is being exacerbated by longer periods of drought and decreased snowfall.
Knowing that our climate is changing due to human activities means that we know how to lessen the effects of future warming. And knowing how we know what causes climate change confirms that our efforts would be meaningful. The situation is serious, but it's not hopeless. Together, we can decide to make a better choice.
Hi, I'm Lori. I study the planets, our solar system, and I especially love volcanoes. And this is Ask NASA. The thing I love the most about our solar system is that it's an incredible natural laboratory. We have so many different types of objects in the solar system, from planets and moons and asteroids and comets. We can study each one of those, and they all have something they can tell us about how the solar system formed or how Earth ended up in its special place. And understanding why the other planets are different from Earth actually helps us better understand how we ended up the way we are today. So this is a globe of Mars right here, and many of the reasons why we're so interested in Mars, there's a lot of different processes going on Mars that help us better understand Earth. A lot of the surface of Mars has been preserved for almost 4 billion years, and so we can study a lot of things on Mars that you can't even find on Earth.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So Perseverance rover is going to drive around and find some of the best rocks it can, drill down into the rock and soil and collect those samples so that on our next mission, Mars Sample Return, we'll be able to bring those back and study them in our laboratories here on Earth. There is volcano on Mars. In fact, there's lots of volcanoes on Mars. The largest volcano we know of in our whole solar system is on Mars. It's called Olympus Mons, and it is so giant that the entire chain of Hawaiian islands could fit inside the crater at the top of that volcano. We see volcanoes really across the solar system on all of our rocky bodies. So on Mercury, we see evidence of lava flows on the surface of Mercury. Even on the moon, we have lava flows that we can see. On Venus, we see the entire surface of Venus is covered with lots of volcanoes and volcanic deposits. So this is a globe of the moon Io. Io is the moon of Jupiter. That's the most volcanically active body in our solar system. And that's because the pull of Jupiter's gravity on Io as it goes around Jupiter tugs and pulls at Io, and that heats up the inside, and that drives volcanoes. The heat needs to be released. This is the volcano Pele. And there's lava flows down here in the middle, but then there's also this big red-orange deposit, which is actually from explosive eruption of the gases that are falling down onto the surface of Io around the volcano. And it has no atmosphere, so if you were to turn it like this and look at this volcano from the side, you see a big umbrella of gas. The particles just come out and then they drop back down. And I started studying volcanoes on Earth about 35 years ago, and then started studying volcanoes on other planets, and that grew into my love of our solar system. So the asteroid belt really contains a lot of leftover material from solar system formation. You can imagine that when the solar system first formed, the particles kind of came together and made bigger particles. Some of those came together and created the planets. We actually find asteroids in lots of different parts of our solar system. We have asteroids that are near Jupiter, the Lucy mission, which is going to launch this year in 2021, and it's going to go study those special asteroids that are trapped in Jupiter's orbit. And then next year we have another mission called Psyche that's going to a particular asteroid called Psyche. It looks to be made mostly of metal, of iron. It may actually be the exposed core of a small planet that may have had its crust blown off by an impact and left that metal core that we can see. There is definitely water on the moon. We know this because we've observed with some of our orbiters being able to identify that there's water molecules on the moon. And in fact, some of these we believe are preserved as water ice, perhaps in these permanently shadowed regions that are very, very cold near the poles. And what we need to do next is to actually go down to the surface of the moon and actually look at that ice up close. And so that's what we're doing with the Artemis mission. We'll be focused on looking for some of that water in the soil of the moon. We have explored really the far reaches of our solar system. We have sent missions to Mercury near the sun and visited all of the planets in our solar system, all the way out even to Pluto. And then one of our missions, called Voyager, actually has 2 spacecraft that have now even gone beyond the edges of our solar system. So we have really explored the whole expanse of our solar system.
Cool. Io and Mars are great.
Let's try it again.
Oh, that's too hot. That was a fastball. She had a fastball.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
Continuing a collaboration in space exploration, space station research heads back to Earth, and highlighting new science from NASA missions. A few of the stories to tell you about this week at NASA. On January 13th at NASA headquarters, Administrator Bill Nelson, Japan's Prime Minister Kishida Fumio, and others were on hand as U.S. Secretary of State Antony Blinken and Japan's Minister for Foreign Affairs, Hayashi Yoshimasa, signed an agreement for a continued collaboration in space exploration between the two nations. A SpaceX Dragon cargo ship undocked from the International Space Station on January 9th with about 4,400 pounds of cargo to be returned to Earth, including valuable scientific experiments. The 241st meeting of the American Astronomical Society featured news that our Webb Space Telescope helped reveal remarkable similarities between distant galaxies from the dawn of the universe and a rare class of small galaxies much closer to us. Our Hubble Space Telescope, Chandra X-ray Observatory, and TESS were also discussed at the meeting. According to an analysis by NASA, Earth's average surface temperature in 2022 tied with 2015 as the fifth warmest on record. The past 9 years have been the warmest years since modern record keeping began in 1880. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
Welcome to Space to Ground. I'm Nilofer Ramji. After nearly a month and a half in orbit, the 26th SpaceX resupply mission is back on Earth, loaded with several tons of scientific cargo. Following a set of commands from ground flight controllers, the Cargo Dragon spacecraft undocked from the Zenit port of the International Space Station's Harmony module at 5:05 p.m. Central Time on January 9th. The resupply mission launched from Florida on November 26th to deliver nearly 4,400 pounds of science and supplies, including 2 new IROSA solar arrays that were installed by spacewalking astronauts in December. 2 days later, the spacecraft re-entered the Earth's atmosphere, making a parachute-assisted splashdown in the pre-dawn hours off the coast of Florida. With Crew Dragon Splashdown, we welcome home several science investigations where researchers can continue their work on Earth. One of these investigations is designed to protect astronauts from high doses of radiation. Crew members wore a special device called AstroRad Vest while performing daily tasks. Astronauts provided feedback on the vest's feel, fit, and range of motion. This feedback will allow the garment developers to improve its design, which aims to provide personal radiation protection for astronauts on Artemis missions and on future travel to Mars. Another returning investigation known as Dynamos compares 2 soil model microbial consortia, one aboard the space station and another here on Earth. Results from this investigation could help researchers develop integrative networks to predict the influence of selection pressure imposed by the space station on microbial community dynamics and functions. Also returning on Dragon are samples of extra virgin olive oil. This investigation will analyze the properties of the flown olive oil samples with controls that were kept on the ground. Olive oil is rich in antioxidants and anti-inflammatory compounds, and provided that the oil maintains its properties in space, it could be beneficial to the health of astronauts on long-term space missions.
Space to ground.
Last month, an external leak was detected from the Roscosmos Soyuz MS-22 spacecraft docked to the International Space Station. That Soyuz carried 3 crew members, including NASA astronaut Frank Rubio, to space on September 21st from the Baikonur Cosmodrome. Roscosmos engineers have determined that the spacecraft is not viable for a nominal crew return. An uncrewed Soyuz spacecraft will replace the current vehicle. That spacecraft, Soyuz MS-23, will launch to the space station on February 20th. And that's Spacegram for this week. For all of the latest on the science taking place aboard the orbiting laboratory, don't forget to follow us on Twitter at ISS_research. Thanks so much for watching. We'll see you next week.
So first on the list is the vehicle control effects, which allow you to convert or return current according to units. Moving forward,
world is full of new and exciting inventions that continue to push the boundaries of technology forward. Every day, it seems something new is announced, developed, and implemented that changes how humans interact. Just in the past few decades, cell phones, internet speed, medical breakthroughs, and the reinvention of basic infrastructure is beginning to change the norms in our everyday lives. But have you considered how these changes in science, engineering, and medicine occur? To most of us, on the outside of these revolutionary practices, it seems like magic when innovations appear in our lives overnight. In reality, it's years of painstaking work, trial and error, and rigorous testing that occurs before a finished product is ever realized. Researchers in the world of engineering and science move in small incremental steps, slowly building a case for these new revelations until they are sure technologies are ready to be shared with the world. In fact, there is an old saying in research, quote, "An amateur works on a task until they get it right, but a professional works on a task until they can't get it wrong," end quote. Fortunately for all of us, over the past few years, NASA, the FAA, and industry have been engineering the next big idea that may completely change how we interact in our world with the implementation of unmanned aircraft. The idea for inclusion of these aircraft is not new. The basic concept for small flying vehicles has been in popular culture and in the limelight for quite some time. But until recently, these vehicles have rapidly accelerated off the drawing board and into the skies. Over the past few years, NASA has been testing and validating research associated with unmanned aircraft through a project called Unmanned Aircraft System Integration in the National Airspace System, or UAS in the NAS project. This project spanned several years and addressed many of the early concerns of how unmanned aircraft would be integrated into our national airspace. After years of study, the UAS in the NAS project has tackled many of the early concerns. But one last big hurdle remains: to successfully demonstrate how unmanned aircraft will work in harmony within the national airspace. With this in mind, the final phase of testing, called the Systems Integration and Operationalization Demonstration Activity, or SIO, has begun in earnest. Throughout our country, at various NASA field centers and other testing locations, NASA has begun in earnest. Throughout our country, at various NASA field centers and other testing locations, NASA has assembled a core strategic group of researchers to analyze and test unmanned aircraft through the SIO demonstration. Some of the key flight activities will include using various sized unmanned aircraft built by 3 different companies to highlight commercial UAS missions that have the potential to provide economic and public benefit to the American people. Throughout the testing, NASA plans to document best practices and lessons learned from the SIO activity and provide it to the UAS community to prepare us for routine commercial unmanned aircraft operations in our communities. On this episode of NASA X, we will take a look back at years of testing and development that have led up to the SIO demonstration flights, and we'll meet the companies that are helping to make these flights happen. This research and engineering has the potential to influence a massive shift in how we receive products and services, and may ultimately make an impact on how people travel and interact in our world. To understand why the NASA team has set up the SIO demonstrations, we first have to look at why integrating unmanned aircraft into the NAS is such a Herculean effort. Here in the United States, we arguably have the best air traffic management system in the entire world. During normal times, around 50,000 flights take off and land daily, with nearly 3 million airline passengers traveling across the more than 29 million square miles that make up the U.S. national airspace system. In that system, close to 15,000 air traffic controllers, 4,500 aviation safety inspectors, and 5,800 technicians operate and maintain services for our National Airspace System, or NAS. It has more than 19,000 airports and 600 air traffic control facilities. In all, there are 41,000 NAS operational facilities and over 71,000 pieces of equipment, ranging from radar systems to communication relay stations. With all of this infrastructure, integrating unmanned aircraft systems into the NAS will be demanding, to say the least. But this integration is of vital importance to our country because these new vehicles will be part of the next revolution in national security and defense, emergency management, science, and in commercial applications. For these reasons and more, NASA set out in 2009 to work on several main objectives for the project that included providing research findings that utilized simulation and flight tests, supporting the development and validation of detect and avoid and command and control technologies, and finally, the SIO demonstrations themselves. Two of the biggest challenges that needed solutions before the SIO demonstrations could take place was in the key areas of detect and avoid and command and control. For detect and avoid, one of the primary safety concerns with integrating these new systems is the inability of remote operators to see and avoid other aircraft. On all flights with pilots on board, the FAA requires the crew to be aware of all other surrounding aircraft, either visually or using onboard instrumentation. So in addition to instruments, the pilot physically looks out of the window to help safely avoid other aircraft. Because unmanned aircraft literally don't have a pilot on board, NASA and its partners worked on concepts and designs that allowed safe operation within the national airspace.
What detect and avoid is since the pilot for an unmanned aircraft is either remote off the aircraft or not there at all in the case of an autonomous aircraft, there is no human eyeball to go see other aircraft. So the technology needs to be developed to use other means, such as radars or cameras, to be able to detect where other aircraft are flying in the proximity of your aircraft, your unmanned aircraft, and then be able to somehow, like a pilot would, avoid those other aircraft. And the way that's done is through developing some mathematical algorithms to be able to direct the aircraft to a location that would be safe. And so that's the kind of research that NASA wanted to focus on, because that was the most critical aspect of how to safely integrate unmanned aircraft into the national airspace that industry writ large could not really understand.
The second hurdle was with command and control. Because unmanned aircraft are completely different from crewed aircraft, new techniques needed to be developed, including improving the avionics on board the UAS and on the ground. These aircraft must have reliable, safe, and secure data connections at all times while operating in the complex environment of controlled airspace.
Similarly, the command and control part of the US and the NAS project is based on the fact that most radio communications that are operated in the airspace now with pilots are voice communication. So it's a pilot talking to an air traffic controller or talking to other pilots, and they use voice to do that. Well, so the aviation spectrum that's been set aside for voice control doesn't work for an electronic control, because if you're going to control the aircraft through some sort of communication methodology, it's got to be done electronically, because you're sending a message to the aircraft to be able to turn or to be able to climb or descend, etc. And so, so the technology that NASA worked on was to develop a radio that could be used in that bandwidth, that spectrum bandwidth, to be able to send electronic messages to and from the vehicle, and thus be able to command the vehicle. So that's why the command and control work that's been done under the UAS and the NAS project is so important.
Over the years, researchers time and time again showed that they had developed the detect and avoid and command and control technology to the point where it could be reliably tested in real-world conditions. Although there were other flight demonstrations throughout this project, the last major hurdle of flying the SIO demonstrations is now at hand. NASA, in partnership with the FAA and industry partners, have begun the demonstrations of potential commercial using different sizes of unmanned aircraft systems for the SIO demonstrations. The goal of SIO is to work toward commercial UAS operations in the NAS. In order to accomplish this goal, NASA has partnered with 3 pioneering companies to conduct flight demonstrations in the NAS that emulate commercial missions and begin working toward Federal Aviation Administration or FAA type certification.
When NASA was selecting the partners for SIO, we went through a partnership process that included the evaluation of a number of candidate partners. And we were looking for some key aspects that these partners could bring to the table. And so the first was really great domain knowledge in unmanned aircraft and associated technologies. The second attribute was knowledge of certification and the knowledge that's really needed to kind of take these vehicles from the concept and early development stages through to becoming a commercial product. And then the third thing we were looking for are viable commercial missions that would be publicly beneficial. We really wanted to showcase how unmanned aircraft can play a role in the future of the world and have a positive impact. There's 3 different companies that are participating in the SIO activity: Bell Atomics Aeronautical Systems and AATI. Bell is bringing their AP-70 unmanned aircraft, which weighs approximately 300 pounds and is capable of vertical takeoff and landing and operations around urban areas. The primary mission that they're focused on is emergency medical in an urban area. General Atomics is utilizing their Sky Guardian unmanned aircraft for multimodal long-endurance infrastructure inspection. That unmanned aircraft weighs approximately 12,000 pounds, so it's much bigger than the others that are participating in SIO, and is intended for an infrastructure inspection mission at altitudes above 10,000 feet. AATI is using their AI Ranger unmanned aircraft, which weighs approximately 180 pounds, for a pipeline inspection mission at lower altitudes between 1,000 and 5,000 feet. And then lastly, throughout this process, we've been collaborating with the FAA, who has provided extraordinary support and helped us to navigate the regulatory process that's in place for these demonstration activities.
The 3 partner companies are each using various sized and different types of unmanned aircraft configured for the SIO demonstrations.
Over the past several years, actually going back probably a couple decades, NASA has been working on UAS. First more in the technical side and now maybe more on the standard side. And I think the SIO activity was looking, or the objective was to address some of the gaps that still remain. And one of the ways that we were able to do that is by partnering with some companies to go after some of these things. The outcome of the demonstrations is to try to help the companies really get their arms around some of these barriers that still exist, work with the FAA to develop the processes, the solutions to be able to address some of these gaps, and then bring it to a place where the industry can learn off of those lessons. The aircraft that are participating in the SIO activity are really pretty unique, and they span quite a range. You've got airplanes that have propulsion systems that are all electric. You've got a turboprop. Another one is a piston powered. So from a propulsion side, they're pretty distinct. And then even if you look at the way that they just operate, you know, one takes off like a conventional airplane would take off from a commercial airport. Another one can basically launch off of almost anywhere and just land on some clearing. And then another one actually can take off also from anywhere, just vertically, and again landing vertically. So quite a range, even in altitudes, the way that they operate. Some of them were designed to operate at lower altitudes. Some of them were designed to be able to go pretty high, even maybe 40,000 feet.
Each company offers a unique perspective and engineering goal in performing the SIO tests.
So Bell's participation in NASA SIO is really about making sure we get the data that the regulators need to be able to understand not just the aircraft requirements, but the system environments for being able to get advanced aerial mobility actually into commercial space, integrated with the rest of aviation in the national airspace. Bell's actually been doing unmanned aerial vehicles for quite some time. From a commercial standpoint, APT is, a sizable vehicle. A little over 300 pounds, carry 70 pounds of payload. It's critical that we get this right so that we are safe and compliant in the airspace, and that's a part of what NASA SIO is about. They're a trusted data provider for the FAA and other regulators to be able to help us understand what really is required for the aircraft, for the airspace requirements, and then for the integration of those systems together. So NASA's involvement helps drive the technology to a high enough level that we have sufficient data for the FAA to make regulations. I would say the way it's being done right now is innovative. You see, NASA leaning forward with electric and hybrid propulsion, as well as, detect and avoid, and some of the things that we need for the airspace. You see the FAA leaning forward based on their small unmanned experience and knowing that we need to get out in front of this time to make sure that we do it right as we get to larger vehicles. And so that partnership and kind of active arrangement of let's discover together and work together towards what's both safe and economically viable as an overall community is really new.
On this particular mission, the APT-70 was armed from a ground control station, then was instructed to initiate a vertical takeoff. Per its design, it then rotated to fly on its wings, where it was nearly silent to the researchers below. It flew at an altitude of 500 feet above ground level, transitioned in and out of Class B airspace, all while staying in constant communication with the ground station through a redundant data link. On board was the prototype airborne detect and avoid system that provided the remote pilot with awareness of air traffic in the vicinity and recommended flight maneuvers. Initial results were promising, with more validation and testing to continue in the future. Another partner, General Atomics Aeronautical Systems Inc., or GA, flew their Sky Guardian aircraft. It had been used for unmanned missions for many years, totaling more than 6 million flight hours. For this NASA mission, a demo aircraft piloted remotely flew for 9 hours from its Gray Butte Flight Operations Facility near Palmdale, California, to Yuma, Arizona. Data was collected from the detect and avoid system to provide situational awareness of air traffic near the Sky Guardian. This system includes a traffic alert and collision avoidance system used in manned aircraft, which fly in civil airspace, and air-to-air radar to detect and track nearby aircraft that may not have active transponders. The particular aircraft in this test may provide services that include hundreds of miles of inspections of rail, power line, communication and canal infrastructure, agriculture monitoring and topological surveys, as well as wildfire and flood monitoring. According to GA CEO Lyndon Blue, quote, GA's work with NASA is opening the eyes of regulators to the safety and utility of unmanned aircraft systems and the performance of certain tasks for public and commercial good, end quote. Researchers believe these types of aircraft will also play an important role during crisis management events, such as wildfire containment. The onboard airborne sensors can see through thick smoke, enabling the craft to inform ground personnel about the location of fire lines so they can deploy resources more efficiently. The SIO demonstration also highlighted how the aircraft can be used for many other civilian and commercial missions as well. The third demonstration flight was a team from American Aerospace Technologies Incorporated, or AATI. Although AATI's craft was considerably smaller than the other test vehicles, its use case was invaluable. It can fly at medium altitudes and carry advanced sensors used to patrol our nation's more than 500,000 miles of midstream pipelines, providing a fundamentally new and unique capability that changes the way we manage health, safety, and the environment, respond to disaster.
The mission itself serves multiple purposes. We're proving out the capability of beyond visual line of sight UAS in the national airspace. And the specific applicability for this mission is that we are looking for ways to make critical infrastructure inspection processes safer and more efficient. And so for this specific mission, the air range off from our launch and recovery site, and we flew downrange along a oil pipeline which is buried underground, and we performed an inspection of the right-of-way of that pipeline. And we are proving out not only the applicability for critical infrastructure itself, but we're proving out the safety case for actually operating UAS in the NAS, not only utilizing the aircraft's technology for flight, but also utilizing different technologies for safety, such as detect and avoid systems, ADSB, and flight radar notification systems for having situational awareness of not only what's in the airspace around us, but being able to tell others in the airspace that we're flying as well. In my opinion, and certify these types of aircraft to fly, you have to prove out three different things. You have to prove out that the aircraft itself is mission capable. You have to prove that the aircraft is dynamically capable to change for different conditions. And you also, most importantly, have to prove out the safety case. And so utilizing different types of technology, utilizing different processes and workflows, building the safety case around operating procedures, and integrating all of these different components aside from the actual flight itself, really build the roadmap and really set the stage for the rest of the industry to say, hey, look, this is what the infrastructure looks like, this is what the framework looks like to do this on an operational basis in the future.
Although the SIO demonstrations are now complete, NASA and industry will continue to move forward with exciting new technologies and hardware built on the foundation of successful data collection and testing from the SIO activity. The future of unmanned aircraft is bright. UAS will continue to advance scientific